A beam of sunlight crosses the distance from the Sun to Earth in just over 8 minutes, yet no object with mass can ever catch it. The closer a spacecraft moves toward that boundary, the stranger measurement becomes onboard clocks fall behind Earth's. Interstellar distances contract, and even the meaning of now changes between observers. At the limit itself, light follows a path with zero proper time, though physics offers no valid viewpoint from which a photon could describe the journey. Where are you watching or listening from, and what time is it there? Perhaps this is playing before sleep, during a quiet study session, or beneath a late-night sky. Leave a comment so the calm space science community can see how far this journey has travelled. Thank you for spending part of your time here. A gentle like, subscription, or share helps calm space science continue creating thoughtful journeys through the universe. The first clock is already moving, and space-time is about to reveal what speed truly changes. Light does not move through empty space at an arbitrary pace. In a vacuum, it travels at exactly 299,792,458 meters per second. That value is not merely a measurement refined by better instruments. It is built into the way modern physics describes space, time, energy, and causality. The symbol often used for it is the letter c, but the deeper point is that this speed belongs not only to visible light, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays all move through a vacuum at the same speed. They differ in wavelength and frequency, yet they share the same propagation limit because all are forms of electromagnetic radiation. The same constant also appears in equations that have nothing to do with lamps, stars, or colour. It connects mass with energy, helps define the structure of space-time, and sets the boundary between events that can influence one another and events that cannot. For that reason, the speed of a light is better understood as a property of the universe than as a special talent of light itself. Before relativity, motion was usually described by adding and subtracting speeds. If a train moved forward and a person inside threw a ball in the same direction, an observer beside the tracks would measure the speed of the train combined with the speed of the ball. This rule works extremely well for ordinary objects. It matches daily experience because familiar speeds are tiny compared with the speed of light. The difficulty appeared when physicists considered light. Experiments showed that light in a vacuum was measured at the same speed regardless of how the source or observer moved. A beam did not behave like a ball thrown from a train. Motion toward the beam did not make the measured speed larger, and motion away from it did not make the measured speed smaller. The result was not a minor exception. It meant that the usual assumptions about distance and duration could not remain unchanged. If every inertial observer measures the same speed of light, then different observers cannot always agree on the length of a path or the amount of time taken to cross it. Space and time have to adjust so that the measured value remains constant. This is the central move of special relativity. The theory begins with two principles. The laws of physics are the same in every inertial frame, meaning every frame moving at constant velocity without rotation or acceleration. The speed of light in a vacuum is also the same for every inertial observer, regardless of the motion of the source or observer. From these simple statements follow time dilation, length contraction, the relativity of simultaneity, and the energy barrier that prevents massive objects from reaching light speed. The limit is therefore not imposed by friction, engineering weakness, or a lack of powerful engines. It arises from the geometry of space-time itself. In relativity, the motion of an object through space cannot be separated completely from its motion through time. Space and time form a single structure called space-time, and every object follows a path through it. Massive objects move along paths that remain inside the local light cone, the region containing all events that can be reached without exceeding the speed of light. Light travels along the boundary of that cone. Anything that would move faster than light would have to pass outside it, entering a region where the normal order of cause and effect becomes difficult to preserve. The light cone is not a physical surface. It is a way of representing which events can be connected. If a star emits a flash, the light spreads outward. Any event reached by that flash lies on the future light cone of the emission. Events inside the cone can be influenced by slower signals or material objects. Events outside it are too far away for any influence travelling at or below light speed to arrive in time. This structure protects causality. A cause can affect a later event only if some signal or interaction has enough time to travel between them without crossing the limit. The speed of light therefore serves as the speed of information. No message, warning, physical disturbance, or transfer of usable influence has been shown to move faster through empty space. This does not mean that every apparent change in nature must crawl across the universe as a visible beam. Fields can extend over large regions, and quantum systems can display correlations between distant measurements. Yet these effects do not allow controllable information to be sent faster than light. The distinction matters because relativity is concerned not only with motion, but with what can produce a consequence elsewhere. Another source of confusion comes from the fact that light often travels more slowly through matter. In water, glass, air, and other materials, an electromagnetic wave interacts with charged particles. The overall propagation of the wave through the material is delayed, so its effective speed is lower than the vacuum value. This does not change the universal constant. Between interactions, the underlying electromagnetic influence still respects the vacuum limit, and no material object is accelerated beyond that limit merely because light is slowed within the substance. Particles can sometimes move through a medium faster than light moves through that medium. When this happens, they produce Cherenkov radiation, a faint glow generated by a kind of electromagnetic shock effect. Even then, the particles remain slower than light in a vacuum. The cosmic speed limit is not the local speed of light in glass or water. It is the invariant vacuum speed. The exact value of this constant now helps define the meter itself. Rather than treating the speed of light as a quantity that must be measured anew each time, modern metrology fixes its value exactly and defines distance through time. A meter is linked to the distance light travels in a specified fraction of a second. This choice reflects how deeply the constant has entered the foundations of measurement. It also shows that the statement light travels at a certain speed depends on units chosen by humans, while the existence of an invariant limit does not. Another system of units could assign the constant a different numerical value, or even set it equal to 1, but the physical relationships would remain the same. What matters is the role the limit plays in comparing space and time. Light speed is also enormous on human scales and slow on astronomical ones. A light signal can circle Earth several times in 1 second. Yet it takes more than 8 minutes to travel from the Sun to Earth. It takes years to cross the distance to nearby stars, tens of thousands of years to cross the Milky Way, and millions or billions of years to travel between distant galaxies. Looking into space is therefore always a view into the past. The Sun is seen as it was minutes earlier. The nearest large galaxy is seen as it was millions of years earlier. Very distant galaxies are observed as they were when the universe was much younger. This delay is not caused by weak telescopes. It is a direct consequence of the finite speed at which information arrives. The universe has no mechanism for delivering an immediate picture of distant events. Even gravity respects this limit. Changes in a gravitational field propagate as gravitational waves at the speed of light. When two dense objects merge, the disturbance in space-time does not announce itself everywhere at once. It travels outward at the same invariant speed that governs electromagnetic radiation. This agreement is important because it shows that the constant belongs to the structure of space-time, not only to one force. The phrase speed of light can therefore be slightly misleading. Light reveals the limit because photons are massless and naturally move along light-like paths. But the constant would remain fundamental even in a universe discussed without visible light. It would still define causal connection, relativistic energy, and the conversion between spatial and temporal intervals. Massive objects, by contrast, always move more slowly than this boundary in any local inertial frame. They can approach it with increasing energy, but the closer they come, the more strongly relativistic effects reshape their measured time, distance, momentum, and energy at low speeds. These changes are too small to notice. At high speeds, they become the dominant features of motion. The cosmic limit is therefore not a wall encountered only at the final instant. Its influence begins earlier, gradually altering every measurement as velocity rises. The fixed speed of light forces space and time to become flexible quantities, and the first clear sign of that flexibility appears in the behavior of moving clocks. A moving object does not carry a private clock and ruler that behaves strangely only because someone happens to watch it. The deeper result of special relativity is that measurements of time and distance depend on the state of motion of the observer making them. This does not mean that reality becomes arbitrary, or that any measurement can be declared correct without rules. It means that space and time are not separate, absolute background shared in exactly the same way by everyone. They are parts of a single structure, space-time, and different observers divide that structure into space and time differently. The effect is difficult to notice in ordinary life because human motion is extremely slow compared with the speed of light. A car, aircraft, or spacecraft may seem fast, yet its speed remains such a small fraction of the cosmic limit that the relativistic corrections are usually tiny. The older Newtonian picture works well under those conditions. In that picture, time passes at the same rate everywhere, and distances remain fixed regardless of who measures them. Motion takes place against a universal stage. Special relativity replaces that stage with a more careful system, in which observers agree on the laws of physics and on the speed of light, but not always on the duration between events or the distance separating them. An event in relativity is something that happens at a particular place and time. A flash occurs, a particle collides with a detector, a clock reaches a chosen reading. To compare what different observers measure, physics uses reference frames. An inertial frame is a frame moving at constant velocity, without acceleration or rotation. No inertial frame is treated as the true frame of rest. A laboratory on Earth may be convenient for one experiment, while a spacecraft moving steadily past it may be convenient for another. Each frame has its own network of clocks and rulers, and each can describe the same events consistently. The disagreement begins when those frames assign different spatial and temporal coordinates to the events. Consider a spacecraft passing a station at constant speed. At the instant their centers align, both observers set a clock to the same reading. Later, a pulse of light is emitted from the middle of the spacecraft and travels toward both ends. For an observer traveling with the craft, the front and rear are equally distant from the source, and the light reaches them at the same time. For an observer on the station, the rear of the spacecraft moves toward one pulse, while the front moves away from the other. Because light has the same speed in the station frame, the pulse reaches the rear first and the front later. Both descriptions obey the same physics. Neither observer is making an error. The difference arises because simultaneity itself depends on motion. This example points toward a broader truth. When observers move relative to one another, a change in measured time is linked to a change in measured distance. The two cannot be adjusted independently. The mathematical relationship that connects the frames is called the Lorentz transformation. It replaces the simpler rules used in classical mechanics. Under the older Galilean transformation, time is unchanged and positions shift according to relative speed. Under the Lorentz transformation, space and time mix. A measurement that is purely spatial in one frame may include a time component in another. This mixing is not a visual illusion or a delay caused by light taking time to reach the eye. Even after observers correct for signal travel time, their measurements can still differ. Relativity concerns the structure assigned to events after those corrections have been made. The invariant quantity is not distance alone or time alone, but the space-time interval. This interval combines spatial separation and temporal separation in a way that all inertial observers agree upon. They may disagree about how much of the separation belongs to space and how much belongs to time, yet the combined interval remains unchanged. In ordinary geometry, different observers can rotate their coordinate axes and assign different horizontal and vertical components to the same line. While agreeing on the line's total length, space-time has a related but distinct geometry. Relative motion changes the division between space and time, while preserving the space-time interval. The comparison is useful only up to a point, because time does not behave exactly like another spatial direction, but it helps show why disagreement between observers does not destroy consistency. The disagreement follows a strict pattern. One consequence is that a moving clock is measured to run slowly. Another is that a moving object is measured to be shortened along its direction of motion. A third is that observers can disagree about whether separated events occur at the same time. These effects are not three independent corrections added onto an otherwise classical universe. They are different expressions of the same geometry. The fixed speed of light forces them to occur together. If time and distance remained absolute, observers moving at different speeds would measure different values for the speed of the same light beam. Because they do not, the coordinates must transform instead. The role of measurement is important here. To measure the length of a moving object, an observer must record the positions of its front and rear at the same time in that observer's frame. Another observer moving with the object uses different definition of which distant events are simultaneous. The resulting lengths differ because the observers do not select the same pair of events for the measurement. In a similar way, measuring how long a process takes requires choosing two events, such as the departure and arrival of a spacecraft, and comparing clock readings. If the events occur at the same place in one frame but at different places in another, the elapsed time need not match. The shortest time between two events is measured by a clock that travels directly from one event to the other without changing inertial motion. This time is called proper time. It belongs to the path through space-time taken by that clock. Proper distance has a related role for events that are simultaneous in a chosen frame. These ideas show why time and distance are not free-floating properties. They are connected to specific measurements, specific observers, and specific paths. This does not reduce physics to opinion. Every observer can calculate what another observer should measure, and the predictions agree when the relative motion is known. If a spacecraft reports that its onboard clock has advanced by a certain amount, Earth-based observers can use relativity to predict that reading. The crew can do the same for clocks on Earth. The equations are symmetrical for observers in uniform relative motion. Each sees the other's clocks as running slowly, and this symmetry does not create a contradiction because comparisons between distant clocks depend on simultaneity. The situation changes when one observer accelerates, turns around, or follows a different path through space-time. Then the symmetry between the paths can be broken, which becomes important in the twin paradox. For now, The central point is that uniform motion alone does not reveal a preferred state of rest. A person inside a sealed spacecraft moving smoothly cannot determine, using only local experiments, whether the craft is at rest or moving at constant velocity. A dropped object falls toward the floor in the same way. Light and mechanical experiments follow the same laws. Motion becomes meaningful only relative to something else. Velocity is therefore relational, but the speed of light remains invariant. This combination is what gives special relativity its unusual structure. Some quantities are frame-dependent, while others remain the same. Energy and momentum can change between frames. The time between events can change. The spatial distance can change. The order of events can even change when those events are too far apart for light to connect them. Yet events linked by a possible causal signal keep the same order for every observer. A cause that can influence an effect cannot be reversed merely by changing frames. Space-time preserves causality by separating event pairs into different categories. Time-like separated events can be connected by an object moving below light speed. Light-like separated events can be connected only at light speed. Space-like separated events are too distant for any causal influence to pass between them without exceeding the limit. Observers may disagree about the timing of space-like separated events, but they cannot use that disagreement to send information into the past. The structure remains coherent because the speed of light marks the boundary. Relativity, therefore, does not say that everything is relative. It identifies exactly what changes and what does not. The laws of physics remain the same. The speed of light remains the same. The space-time interval remains the same. Local cause and effect remain protected. What changes is the way different observers assign space and time to a shared sequence of events. As velocity rises, these differences become larger and more measurable. Clocks separate in their readings, lengths contract along motion, and distant events lose any universal order of simultaneity. The first of these effects is time dilation, where the passage of time itself becomes a measurable part of relative motion. Time dilation is one of the clearest consequences of special relativity, because it can be measured directly with clocks. When two observers move relative to one another at constant velocity, each finds that the other observer's clock advances more slowly than a clock at rest in the local frame. This difference is not caused by mechanical damage, weak batteries, signal delay, or an error in observation. Every physical process inside the moving system is affected in the same way. Atomic vibrations, chemical reactions, biological aging, particle decay, and electronic timing all proceed according to the same reduced rate when measured from the other frame, inside the moving spacecraft. However, nothing feels slowed. The crew's clocks operate normally, thoughts proceed normally, and every local experiment gives ordinary results. Time dilation appears only when the passage of time along one path through space-time is compared with the passage of time along another. A useful way to understand the effect begins with a simple device called a light clock. The device contains two mirrors facing each other, with a pulse of light moving back and forth between them. Each round trip can be treated as one tick. For an observer travelling beside the clock, the light moves straight upward and downward between the mirrors. If the distance between the mirrors is known and the speed of light is fixed, the duration of each tick can be calculated. Now consider an observer watching the same clock move sideways at high speed. During the time the light travels from one mirror to the other, the entire device changes position. The light therefore follows a longer diagonal path across the observer's frame. The light cannot move faster to complete this longer path, because every inertial observer measures the same vacuum speed. The only quantity that can change is the measured duration of the tick. The moving clock must take more time between reflections. The same reasoning applies on the return journey, so the full cycle is longer for the outside observer. This light clock is not a special case. Relativity requires every reliable clock moving with it to slow by the same amount. If different clock mechanisms slowed by different factors, their disagreement could reveal absolute motion, which special relativity does not permit. A mechanical clock, an atomic clock, and a biological organism all follow the same local time because time dilation belongs to space-time rather than to the internal construction of the clock. The size of the effect is determined by the Lorentz factor, a quantity that depends on the object's velocity relative to the observer. At low speeds, the factor is extremely close to 1, so time dilation is almost undetectable. As the velocity rises, the difference grows. At half the speed of light, the change is measurable but still moderate, at 9/10 of the speed of light. The moving clock advances at less than half the rate assigned by the stationary frame. At 99% of light speed, the contrast becomes much larger. A short period aboard the spacecraft can correspond to a much longer period outside it. As the speed approaches the light limit, the Lorentz factor grows without bound, and the amount of outside time associated with a fixed interval of onboard time becomes increasingly large. The correct comparison depends on which pair of events is being examined. Suppose a spacecraft passes Earth, and both an onboard clock and an Earth clock read 0 at the moment of passage. The spacecraft then continues at constant velocity. In the Earth frame, the onboard clock runs slowly. In the spacecraft frame, the Earth clock also runs slowly. This symmetry can appear contradictory, but the contradiction comes from assuming that both observers share the same definition of distance simultaneity. They do not. Each observer uses a different set of distant events as occurring at the same time. As long as the two remain separated and move inertially, there is no single direct comparison of their clocks at one location after departure. Their descriptions remain internally consistent. A decisive difference appears only if one observer changes direction and later reunites with the other. The two clocks can then be compared at the same event, and the clock that followed the path with less proper time will show the smaller reading. That result becomes central to the twin paradox, but the underlying principle is already present here. Time dilation is not simply about how an object looks from far away. It is about how much proper time accumulates along different paths through space-time. Proper time is the duration measured by a clock that travels directly between two events. Every object with mass carries its own proper time along its path, when relative motion changes that path. The amount of proper time between departure and reunion can also change. This effect has been confirmed in many experiments. Unstable particles provide one of the most direct examples. Muons are produced naturally when high-energy cosmic rays strike atoms in Earth's upper atmosphere. A muon at rest survives for only a very short average time before decaying. Using ordinary non-relativistic reasoning, many atmospheric muons should disappear long before reaching the ground. Yet large numbers are detected at the surface. From Earth's frame, the fast-moving muons experience time dilation, so their internal decay process proceeds more slowly, and they survive long enough to travel farther. From the muon's frame, its lifetime remains normal, but the atmosphere is length contracted, reducing the distance to the ground. Both descriptions lead to the same observed result. Particle accelerators show the same pattern under controlled conditions. Particles moving close to light speed remain in unstable states much longer than identical particles at rest. Their extended lifetimes follow the relativistic prediction with high precision. Atomic clocks provide another confirmation. Clocks flown on aircraft or carried aboard satellites accumulate slightly different amounts of time from clocks left on the ground. In these cases, both special relativity and general relativity must be considered. Motion causes the travelling clock to run more slowly through special relativistic time dilation, while differences in gravitational strength alter clock rates through gravitational time dilation. Satellite navigation systems must correct for both effects. Without those corrections, their timing errors would grow and position calculations would quickly become inaccurate. Relativity therefore operates not only in distant galaxies or extreme laboratory experiments, but within technology used every day, near light speed. The consequences would become far more pronounced. A spacecraft travelling to a distant star could take many years according to clocks on Earth, while the crew experiences a much shorter duration. This does not mean the spacecraft crosses space faster than light. Earth still measures its speed below the limit, and the journey still requires at least as much Earth time as light would need to cover the distance. The shorter onboard duration results from the way time and distance transform together. In the crew's frame, the distance to the destination is contracted, while Earth observers describe the distance as unchanged and the onboard clock as slow. Neither frame is more correct. They are different descriptions of the same departure and arrival events. As velocity draws closer to light speed, the traveller's elapsed time can become very small compared with the time measured at rest relative to the endpoints. A journey spanning decades or centuries in one frame could occupy only years for the travellers, provided an enormous amount of energy could be supplied and the acceleration could be survived. This creates a practical form of travel into the future. A crew returning from a relativistic voyage could find that much more time had passed on Earth than aboard the ship. No physical law would allow them to reverse the process and return to an earlier Earth time. Time dilation changes the rate at which different paths accumulate time, but it does not by itself permit travel into the past. The effect also becomes stronger continuously, rather than switching on at a particular velocity. There is no sudden threshold where ordinary time ends and relativistic time begins. Relativity applies at every speed. The difference is that at familiar velocities the correction is too small to notice without precise instruments. As speed rises, the correction becomes more important until it dominates the comparison. At exactly light speed, the mathematical expression used for massive objects no longer gives a finite time dilation factor. The factor diverges, indicating that the light speed boundary cannot be reached by an object with mass through ordinary acceleration. For light itself, the situation requires different language. A photon does not possess a valid inertial rest frame, so its behaviour cannot be described by imagining a clock moving alongside it. Along a light-like path, the proper time between emission and absorption is 0, but this does not mean a photon observes the universe in a frozen instant. Observation requires a physical frame, and no such frame exists at light speed. Time dilation therefore approaches an extreme limit without creating a meaningful viewpoint at that limit. The central result remains grounded in measurable comparisons. Moving clocks accumulate less time between shared events, and the difference increases as their speed approaches the universal boundary. Time has not become unreliable. It has become local, tied to motion, and to the path taken through space-time. The same structure that reduces elapsed time for a fast traveller also changes the measured distance ahead, leading directly to length contraction. Length contraction is the spatial counterpart of time dilation. When an object moves relative to an observer, its measured length becomes shorter along the direction of motion. The effect does not compress the object in every direction, and it does not mean that the object feels pressure or suffers physical damage simply because it is moving. In its own rest frame, the object keeps its normal dimensions. A spacecraft crew measuring the distance from the front of the cabin to the rear would obtain the same result before launch, during uniform motion, and after slowing down. The contraction appears only when the spacecraft is measured from a frame in which it is moving, like time dilation. This is not an optical illusion caused by delayed light or an error in perspective. It remains after the observer has corrected for the travel time of light and calculated the positions of the object's endpoints within a single reference frame. The reason lies in the way length must be measured. To determine the length of a moving object, an observer records the position of its front and rear at the same time in that observer's frame. This requirement seems simple, but simultaneity is not shared universally. Another observer moving with the object uses a different set of distant events as simultaneous. The two measurements therefore compare different pairs of events, and they need not produce the same length. The proper length of an object is the length measured in the frame where the object is at rest. This is its greatest measured length. Observers who see the object moving measure a shorter value along the direction of travel. The amount of contraction is controlled by the same Lorentz factor that governs time dilation. At ordinary speeds, the change is extremely small. A moving aircraft, train, or planet is contracted in principle, but by an amount far below ordinary detection. As the speed rises toward the speed of the light, the contraction becomes substantial. At half-light speed, the difference is modest. At 9/10 of light speed, the moving length is less than half its proper value. Closer still to the limit, a long object can be measured as dramatically shorter from the outside frame. This does not mean that matter is crushed into a thinner form. Every atom within the object is at rest relative to its neighbouring atoms in the object's own frame, and local distances remain normal there. The change belongs to the comparison between frames, not to a universal deformation that all observers agree has happened. A familiar thought experiment makes the distinction clear. A long pole approaches a barn at relativistic speed. In the barn's frame, the pole is length contracted and may fit entirely inside the barn for a brief interval, allowing both doors to be closed at the same time in that frame. In the pole's frame, the barn is moving and is therefore shorter, so the pole cannot fit inside it at any one moment according to that frame. There is no contradiction because the events of closing the two doors are not simultaneous in the pole's frame. One door closes before the other. The argument is resolved not by choosing which object is truly contracted, but by recognizing that each frame has its own definition of simultaneity. Length contraction and the relativity of simultaneity are therefore inseparable. The effect becomes especially important when considering travel between stars. From Earth's frame, the distance to a destination remains the distance measured between the departure point and arrival point, while those endpoints are at rest relative to one another. A spacecraft moving toward the destination crosses that distance at a speed below light speed. Earth observers may calculate that the trip requires decades, centuries, or longer, depending on the destination and the spacecraft's velocity. The crew, however, does not assign the same distance to the journey. In the spacecraft frame, Earth and the destination are moving in the opposite direction. Their separation is contracted along the direction of motion. The crew therefore measures a shorter distance and can reach the destination in less onboard time without exceeding the speed of light. The two descriptions fit together exactly. Earth says the spacecraft crosses a long distance while its clocks run slowly. The crew says its clocks run normally, while the distance between Earth and the star is shortened. Both calculate the same departure event and the same arrival event. Neither description allows the spacecraft to overtake a light beam. Suppose a star is several light years away in Earth's frame, and a spacecraft travels at a speed very close to light speed. Earth observers still see the voyage take several years, because the ship moves below the limit. On board the craft, the distance may be contracted to a fraction of its Earth frame value, and the elapsed proper time may be much smaller. The stronger the Lorentz factor, the shorter the measured journey in the traveller's frame. This relation is not an additional benefit separate from time dilation. It is the same relativistic structure viewed through spatial measurement rather than temporal measurement. The reduction in distance is exactly what is needed to make the shorter onboard travel time consistent with a local speed that remains below light speed. Interstellar travel therefore becomes less restrictive for travellers than it appears from the frame of the planets they leave behind. A voyage across part of a galaxy could, in principle, fit within a human lifetime if the spacecraft moved sufficiently close to light speed. The external universe would age far more during the trip. The challenge is not a violation of relativity, but the immense energy required to reach such velocities, the need to accelerate and decelerate, and the severe interaction with dust, gas, and radiation. Length contraction does not remove those obstacles. It only changes the distance assigned within the traveller's frame. The same principle affects objects encountered during the journey. In the spacecraft frame, the density of material ahead can increase because a region of interstellar space is contracted along the direction of travel. Particles that are widely separated in the rest frame of the galaxy may appear packed into a shorter distance. Their energies are also transformed, making even sparse gas a serious hazard at extreme speed. The contracted route is therefore not an empty shortcut. The physical environment is changed by the same relative motion that shortens the destination distance. Length contraction must also be distinguished from how a rapidly moving object looks in a photograph. A camera does not record all parts of an extended object at the same instant in the camera's frame. Light from different points takes different amounts of time to arrive. At relativistic speeds, this can produce apparent rotation, distortion, and unusual brightness patterns. The calculated length contraction is obtained only after these light travel effects are removed, and positions are compared simultaneously in one frame. An object may therefore look different from the simple flattened form suggested by a diagram, even though its measured relativistic length is shorter. The distinction between visual appearance and physical measurement becomes increasingly important at near light speed, where aberration and Doppler effects strongly reshape the observed scene. There is also no single statement that an object is contracted without naming the frame of measurement. A spacecraft is not contracted relative to itself. Earth is not contracted relative to Earth. Each is contracted only from frames in which it moves. This frame dependence often feels unfamiliar because ordinary language treats length as a permanent property. Relativity replaces that assumption with a more precise one. Proper length belongs to the rest frame, while other inertial frames obtain related values through the Lorentz transformation. The object does not possess one universal length valid for every observer. It possesses a space-time history from which different observers construct spatial measurements. At the limit of light speed, the contraction formula for a massive object would drive its measured length along the motion towards zero. That mathematical tendency does not describe a reachable state for matter. A massive spacecraft cannot be accelerated all the way to light speed, so it never requires a frame in which the external universe has collapsed to no distance at all. Light itself also cannot be assigned a valid rest frame from which to measure a contracted universe. The limiting behavior shows how the equations approach the boundary, but it does not create a physical viewpoint located on that boundary. For any attainable speed below light, however, the contraction is finite and consistent. Distances can become much shorter for the traveller while remaining unchanged for the departure and arrival worlds. This is why a journey that appears impossibly long from one frame can occupy much less proper time in another without breaking the cosmic speed limit. The result depends on a deeper change in the meaning of measurement. To say that two endpoints define a distance requires them to be located at the same time, and different observers do not agree on which distant events share that time. Once simultaneity becomes relative, length can no longer remain absolute. The shrinking of a relativistic journey is therefore not an isolated curiosity. It is evidence that space and time are joined, and that a change in one cannot occur without a corresponding change in the other. The next step is to examine the principle beneath both effects, the absence of a universal presence shared across the universe. The relativity of simultaneity is the point where special relativity most clearly changes the ordinary meaning of the present. In daily life, two events are usually called simultaneous when they happen at the same time. That definition seems simple because people moving at ordinary speeds can synchronize clocks and ignore the tiny corrections produced by relativity. At high relative velocity, however, the phrase at the same time becomes dependent on the observer's frame of motion. Two events that occur simultaneously in one inertial frame may occur at different times in another. This is not caused by confusion, poor instruments, or the delay required for light to reach an observer. It remains true after all signal delays have been calculated and removed. The disagreement belongs to the structure of space-time itself. To define simultaneity across a distance, an observer needs more than one clock. A clock beside a single event can record when that event occurs. But separated events require a network of clocks distributed through space. Those clocks must be synchronized according to a clear procedure. In an inertial frame, one standard method is to place a light source midway between two clocks and send pulses toward both of them. Because light travels at the same speed in both directions within that frame, equal travel distances imply equal travel times. If the pulses reach the clocks together and the clocks are set consistently, events occurring when the clocks show the same reading are defined as simultaneous in that frame. Another observer moving relative to the clocks does not generally accept that synchronization. The clocks are moving in the second observer's frame, and the light pulses do not meet them under the same conditions. One clock moves toward its pulse while the other moves away. Since the speed of light remains unchanged, the second observer concludes that the clocks were not synchronized from the beginning. Both observers agree on the speed of the pulses. They disagree about the timing assigned to the distant clocks. A train thought experiment makes the result more concrete. A long train moves at constant velocity past a platform. Two flashes occur at the front and rear of the train at positions equally distant from an observer standing at the midpoint of the platform. The platform observer receives the flashes together and, after accounting for the equal distances, concludes that the emissions were simultaneous in the platform frame. An observer at the midpoint of the moving train is carried toward the flash from the front and away from the flash from the rear. The train observer receives the front flash first. After correcting for the changing distances, the train observer still concludes that the front flash was emitted before the rear flash in the train frame. Both conclusions are correct within their respective frames. The events are simultaneous for the platform but not for the train. The effect is symmetrical. If two flashes are arranged to be simultaneous in the train frame, the platform observer assigns different emission times to them. Neither frame has access to a universal clock that can settle the dispute. Special relativity does not contain a preferred inertial frame whose definition of the present overrides all others. Every inertial frame can synchronize its own clocks consistently, and each obtains a different division of space-time into layers of simultaneous events. This frame dependence explains why time dilation and length contraction fit together without contradiction. A moving clock appears slow, yet the moving observer also sees the other frame's clocks as slow. The symmetry remains possible because each observer compares the distant clock with a different set of local times. When the observers ask what a faraway clock is reading now, the word now refers to different distant events in each frame. The two measurements are built from different simultaneity conventions required by the same relativistic geometry. Length measurements depend on the same issue. To measure a moving spacecraft, an observer must record the positions of its front and rear simultaneously. Another observer moving with the spacecraft uses a different set of simultaneous events and obtains the proper length instead. The contraction follows from the fact that the two frames select different endpoint events when defining the object's length. This is why the pole and barn thought experiment has no contradiction. In the barn frame, both doors can close at the same time while the moving pole is contracted inside. In the pole frame, the doors do not close together. The rear door closes and opens before the front door closes. What appears to be one simultaneous action in one frame becomes a sequence in another. The order of separated events can therefore depend on motion, but only under specific conditions. If two events are close enough in space-time for a light signal or slower influence to travel from one to the other, every observer agrees on their causal order. A cause cannot become its own effect merely because another observer is moving. Such events are time-like or light-like separated. Different ordering is possible only for space-like separated events, which are too far apart for any signal travelling at or below light speed to connect them. If one observer says a distant explosion occurred before another distant explosion, another moving observer may reverse that order, but neither explosion could have caused the other. The absence of a causal link allows their time order to vary without contradiction. Relativity therefore removes a universal present while preserving local causality. Each observer has an immediate local now at a single event. But extending that present across distance space requires a choice of inertial frame. On Earth, this distinction is normally hidden because relative speeds are low and distances are modest. Across interstellar distances, the idea of a shared cosmic present becomes much harder to maintain. A statement about what is happening now on a planet many light-years away depends on how distant clocks are synchronized and on the observer's motion. No observation reveals the planet's present directly, because every signal arrives from its past, even after calculating what might be happening there according to a chosen frame. Another observer moving differently can assign a different set of distant events to the same local moment. This does not mean that the distant planet lacks a real physical state. It means that the question of which distant state is simultaneous with a local event has no frame-independent answer. The distinction becomes especially important in discussions of faster-than-light travel or communication. If a controllable signal could move outside the light cone, some observers could describe the signal as arriving before it was sent. By combining such signals between moving frames, it could become possible in principle to create a chain in which information returns to an earlier event. This is one reason the speed of light is closely tied to causality. The limit does more than restrict how quickly objects cross space. It prevents disagreements about distant timing from becoming usable contradictions. As long as all influences remain within or on the light cone, observers may disagree about distant simultaneity, while agreeing on every physically connected sequence of cause and effect. The lack of a universal present also changes the common picture of the universe as a single three-dimensional arrangement that updates everywhere at once. Relativity describes a four-dimensional space-time containing events and their relationships. Different observers move through that structure along different paths and divide it into space and time in different ways. One frame's present is tilted relative to another frame's present when represented on a space-time diagram. The tilt grows with relative velocity, which is why simultaneity differences become more pronounced near light speed. This geometric description does not require the future to be known, or human choice to be an illusion. It states only that the separation of events into universal past, present, and future is not as simple as classical physics assumed. Events within a local light cone have a definite causal relation. Events outside it cannot be assigned one shared time order by every observer. Near light speed, these consequences become large enough to shape entire journeys. Earth and a departing spacecraft may disagree not only about how fast clocks run or how long distances are, but also about which events on a distant star are occurring at the same time as departure. As the spacecraft changes velocity, its assignment of distance simultaneity changes as well. During a turnaround, the set of Earth events considered simultaneous with the traveller can shift substantially, helping explain why the twin paradox does not reduce to a simple claim that each twin sees the other aging slowly. The change of frame changes the traveller's distant time assignment. Simultaneity is therefore the link that connects the major effects of special relativity into one coherent system. Time dilation describes differing clock rates. Length contraction describes differing spatial measurements. Relativity of simultaneity explains why those differences can coexist without selecting a preferred observer. Once this is understood, the idea of a universal cosmic now gives way to a more precise boundary. The universe does not provide one present shared across all distances. It provides local events, causal connections, and frame-dependent ways of arranging what lies beyond immediate contact. That structure remains consistent only because no massive object or controllable signal can cross the light speed boundary, which leads directly to the energy barrier faced by matter as it accelerates toward the limit. A spacecraft with NMS can be accelerated to higher and higher speeds, but each increase becomes more difficult as the velocity approaches the speed of light. At ordinary speeds, the relationship between force, energy, and motion is close to the one described by classical mechanics. Adding energy produces a fairly direct increase in speed. Near the relativistic limit, that pattern changes. The spacecraft continues to gain energy and momentum, yet a shrinking fraction of the added energy appears as an increase in velocity. The speed moves closer to the boundary without ever reaching it. This is not a weakness of engines or materials. Even an ideal spacecraft in empty space, supplied with perfectly directed energy, would face the same limit because the barrier is built into the structure of space-time. An older explanation sometimes says that an object becomes more massive as it accelerates. That language can be misleading. In modern treatments of relativity, the rest mass of an object remains constant. A spacecraft does not acquire more rest matter simply because it moves quickly relative to Earth. What increases is its relativistic energy and momentum as measured in the Earth frame. These quantities become increasingly large as the speed approaches light speed. The resistance to further acceleration is therefore not caused by matter physically swelling with new mass. It comes from the relativistic relationship between velocity, momentum, and energy. At low velocity, doubling the momentum of an object nearly doubles its speed. At high velocity, doubling the momentum can produce only a small change in speed. The object still responds to force, but its velocity approaches the limit more slowly. This behavior is governed by the Lorentz factor, the same quantity that controls time dilation and length contraction. As velocity rises, the factor rises. Near light speed, it grows very rapidly. The energy required to move a massive object closer to the limit becomes correspondingly large. At exactly light speed, the Lorentz factor would become unbounded. The energy and momentum required for a massive object to reach that state would also become unbounded. No finite engine, fuel supply, field, or physical process can provide an infinite amount of energy. The object can therefore approach the speed of light as closely as available energy permits, but it cannot complete the final step. This conclusion applies even to very small particles. Electrons and protons in accelerators can be pushed to speeds differing from light speed by only a tiny fraction, yet they still remain below it. When more energy is supplied, the increase appears mainly as greater momentum and collision energy, rather than a noticeable increase in speed. Modern particle accelerators demonstrate this directly. Charged particles circle through magnetic fields while electric fields repeatedly increase their energy. As the particles become relativistic, their speed changes very little, although their momentum continues to grow. The magnetic systems must respond to that increasing momentum to keep the particles on the intended path. When the beams collide, the stored energy can produce new particles, heat, and radiation. It does not carry the original particles through the light speed boundary. The accelerator is therefore not failing to provide enough force. It is revealing the way force acts under relativistic conditions. The closer a massive particle comes to light speed, the more energy is required for each smaller gain in velocity. The distinction between massive and massless particles is central. Particles with non-zero rest mass must move below light speed in every local inertial frame. Massless particles, including photons in a vacuum, move at light speed. They do not begin at rest and accelerate until they reach the limit. A photon is created already travelling along a light-like path, and it continues at that invariant speed until it is absorbed or otherwise interacts. It cannot be slowed to a lower vacuum speed while remaining a freely propagating photon, just as a massive particle cannot be accelerated to the light-like state. The two classes occupy different kinds of paths through space-time. Massive objects follow time-like paths. Light follows light-like paths. Ordinary acceleration can change the velocity of a massive object within the time-like region, but it cannot move that path onto the light-like boundary. The barrier works in both directions. A massive object cannot be pushed up to light speed, and a massless particle cannot be placed at rest. This separation is not merely mathematical. It protects the causal structure established by the light cone. A massive object moving below light speed remains inside the cone and can pass from one event to another through an ordinary sequence of causes and effects. Light travels on the boundary. A hypothetical object moving faster than light would lie outside it, where different observers could disagree about the temporal order of its departure and arrival. Preventing ordinary matter from crossing the boundary therefore helps preserve the shared order of causally connected events. Even before the energy requirement becomes overwhelming, practical barriers make near light speed travel extremely demanding. A spacecraft must carry or receive enough energy to accelerate not only its structure, but also its fuel, shielding, life support systems, and payload. If the fuel is carried on board, accelerating the fuel itself adds to the energy burden. A rocket must expel momentum in the opposite direction, and its available performance depends on the speed and efficiency of that exhaust. Conventional chemical reactions release far too little energy per unit of fuel for extreme relativistic travel. Nuclear reactions release much more, and matter-antimatter annihilation offers a still greater theoretical energy density. But even these do not remove the relativistic rise in required energy. They only determine how closely a chosen spacecraft might approach the limit before its resources are exhausted. External propulsion concepts, such as laser-driven sails, avoid carrying all the energy source on board, but they still face the same fundamental asymptote. No matter how powerful the beam becomes, a sail with mass remains below light speed. Acceleration also has biological and structural consequences. A spacecraft could reach a high velocity gradually while maintaining a tolerable onboard acceleration, but the process would require time and distance. Rapid acceleration would place stronger forces on the crew and vehicle. Slowing at the destination would require another large energy expenditure. The complete journey must account for departure acceleration, long-distance travel, and deceleration rather than treating the target velocity as a freely available starting condition. Relativity can shorten the experienced duration of the cruise, but it does not eliminate the engineering needed to enter and leave that motion. The environment ahead becomes another limit. Interstellar space is thin but not perfectly empty. It contains atoms, ions, dust grains, photons, and cosmic rays. At modest spacecraft speeds, many of these encounters are manageable. At a large fraction of light speed, particles that are low in energy in the galaxy's rest frame appear highly energetic in the spacecraft frame. A single atom can strike with the character of ionizing radiation. Dust grains can release concentrated energy on impact. Light from the forward direction is blue-shifted, raising its frequency and energy. Shielding must absorb or redirect these hazards, yet shielding adds mass. An added mass increases the energy required for acceleration. Near-light travel therefore creates a connected set of problems, rather than one isolated demand for a faster engine. The speed limit itself remains absolute even when some motions appear to exceed it. A spot of light swept across a distant surface can move faster than light, because the spot is not a single object travelling from one location to the next. Different photons illuminate different places, so no material body or controllable signal crosses the surface at the apparent speed. The separation between distant galaxies can also increase faster than light, because cosmic expansion changes the scale of space between them. This is not a galaxy moving locally through nearby space faster than a light beam. General relativity allows the geometry of large-scale spacetime to evolve while local objects still obey the light speed limit. Similar care is needed with quantum entanglement. Measurements on entangled systems can display correlations across great distances, but those correlations cannot be controlled to transmit a message faster than light. None of these cases provides a method for accelerating matter through the relativistic barrier. The limit is local and causal. In any small region where gravity can be neglected and an inertial frame can be defined. Light in a vacuum moves at the same invariant speed, and massive objects move more slowly. Gravity can bend paths, alter clock rates, and change global distances, but it does not give a nearby massive object permission to overtake light. The final barrier is therefore better understood as an asymptote than as a wall. A wall can be reached and touched. An asymptote can be approached indefinitely while remaining unattainable. Every additional supply of energy can move a spacecraft closer to light speed, but the required energy rises more quickly than the remaining gain in velocity. The journey toward the limit continues without a final arrival. Matter remains on one side of the boundary, while light occupies the boundary itself. That distinction leads to a more delicate question. If a photon travels along a path for which the proper time between emission and absorption is zero, it may seem natural to ask what the passage of time is like for light. Relativity allows the path to be described, but it does not allow a valid observer to stand on it. A photon can cross the distance between the Sun and Earth in a little more than 8 minutes as measured by clocks at rest with Earth. It can travel from the nearest stars over several years, from the centre of the Milky Way over tens of thousands of years, and from distant galaxies over spans longer than human civilization has existed. Those durations are real in the frames where the distances and clocks are defined, yet relativity assigns zero proper time to the path of light between emission and absorption. This result is often summarized by saying that light does not experience time, but that sentence can create more confusion than clarity. It suggests that a photon possesses a viewpoint, carries a clock, and observes the universe in a motionless instant. Special relativity allows none of those ideas to be stated literally. The proper time along a light-like path is zero, but there is no valid inertial frame in which a photon is at rest. Without such a frame, there is no physical observer whose measurements can be called the photon's experience. The distinction begins with proper time itself. For a massive object, proper time is the duration measured by a clock moving with that object. A spacecraft can carry an onboard clock from departure to arrival, and the reading on that clock records the proper time along the spacecraft's path. A person, a planet, or an unstable particle can do the same in principle, because each follows a time-like path through space-time and has a rest frame at every moment of unaccelerated motion. Light follows a different kind of path. The spatial distance it covers and the coordinate time that passes are related exactly by the speed of light. In the geometry of special relativity, those contributions cancel in the expression for the spacetime interval. The interval along the path is light-like, and the associated proper time is 0. This statement is precise. It describes the structure of the path between two events. It does not describe a clock attached to the photon, because no clock can move beside light while remaining at rest relative to it. To construct an inertial frame, an observer needs a consistent system of rulers and synchronized clocks that moves below light speed relative to other inertial frames. The Lorentz transformation connects such frames. As the relative speed approaches light speed, the Lorentz factor grows without limit. At the boundary itself, the transformation ceases to produce a valid frame. Lengths along the direction of motion approach 0 in the limiting calculation. Time dilation becomes unbounded, and the ordinary separation of space and time becomes singular. This is not evidence for a strange but usable photon frame. It is evidence that the procedure for building an inertial frame cannot be extended to light speed. The limit can be approached mathematically from below, but it cannot be occupied by a massive observer. This is why phrases such as "from the photon's perspective" must be treated carefully. They may serve as informal shorthand for the fact that proper time is 0 along a light-like trajectory, but they should not be taken as a literal description. A perspective requires an observer, and an observer requires a physically meaningful frame. A photon has energy, momentum, polarization, and a path through space-time. But relativity does not assign it a rest clock or a rest coordinate system. The photon is not a tiny traveller watching the universe pass by. It is a quantum of the electromagnetic field propagating along a null direction. The word null is another name for a space-time interval of 0. The same idea applies to any massless excitation moving in a vacuum. If it follows a light-like path, the proper time between events on that path is 0. The 0 interval does not mean that the emission and absorption events are identical. They can be separated by an enormous distance and by a long coordinate time in the frame of a planet or galaxy. What remains 0 is the invariant combination of that distance and duration. Different inertial observers can disagree about the distance travelled and the time elapsed, but all agree that the path is light-like. One observer may measure a lower photon energy and another a higher one because of relative motion. They may disagree about the wavelength, frequency, and direction of the light. They do not disagree about its vacuum speed or about the classification of the interval. The same two events remain connected by light for every inertial observer. This agreement shows why proper time is not simply another word for elapsed coordinate time. Coordinate time belongs to a chosen frame. Proper time belongs to a time-like path and can be recorded by a clock travelling along it. A light-like path has no such travelling clock. Assigning 0 proper time is therefore a statement about geometry, not about a suspended internal process. A photon also does not decay through an internal sequence measured by its own clock, in the way an unstable massive particle does. It can be absorbed, scattered, red-shifted, or blue-shifted through interactions and changing space-time conditions. But these changes are described from physical frames that remain below light speed. Consider light emitted by a distant galaxy and detected by a telescope after billions of years according to cosmological clocks. During that journey, the expansion of the universe can stretch the wavelength of the light. Its energy at detection may be far lower than at emission. The route may be bent by gravitational fields, and the photon may pass through regions of very different density and curvature. None of this requires time to pass in a photon rest frame. The history is described by the sequence of spacetime regions crossed by the light-like path and by the measurements of observers along or near that route. General relativity extends the same principle into curved spacetime. Locally, light still follows null paths and moves at the invariant speed measured by freely falling observers. Globally, the path can curve because spacetime itself is curved. The proper time along that null path remains zero, even though distant observers may assign a substantial travel time. Gravitational time delay, cosmological expansion, and lensing can all change the coordinate description without creating a valid frame for the photon. The absence of a photon frame also resolves several misleading conclusions. It is sometimes claimed that the entire universe is compressed to zero distance for light. That statement comes from taking length contraction to its limiting value, but length contraction is defined between inertial frames, and the light speed limit is not an inertial frame. A massive traveller moving extremely close to light speed can measure a very short distance to a destination, because the distance is strongly contracted in that traveller's frame. As the speed increases, the measured distance can become smaller, and the proper travel time can become shorter. The limiting equations approach zero, but the final step cannot be promoted into a physical observation made by light. The limit describes what happens to a sequence of valid massive frames as their speeds increase. It does not create one more frame at the endpoint. A similar caution applies to the idea that emission and absorption happen at the same moment for a photon. They are connected by zero proper time, but they are still distinct events in space-time. Their separation can carry causal structure. The emission can influence the absorption, because light travels from one to the other. Calling them the same moment suggests a single clock reading both events, yet no clock follows that path. The more accurate statement is that no proper time elapses along the null trajectory. This wording preserves the geometry without inventing an observer. Quantum physics adds another layer without changing the relativistic limit. Photons are not always best described as small localized objects following perfectly definite classical tracks. They can spread as quantum states, interfere, and be detected probabilistically. In many situations, however, the propagation of light can still be associated with null paths, or with combinations of such paths. Quantum electrodynamics remains compatible with special relativity and does not supply a hidden photon viewpoint. The theory predicts amplitudes and interactions as measured in ordinary physical frames. It does not ask what the photon sees. This restraint is scientifically useful because it separates meaningful questions from grammatical ones. Physics can ask how much time an Earth clock records, how much time a spacecraft clock records, what wavelength an observer measures, how a gravitational field changes the signal, or whether two events are time-like, space-like, or light-like separated. It cannot assign observations to a frame that the theory itself does not permit. The phrase light does not experience time may remain useful only when followed by its precise meaning. The proper time along a light-like path is zero. While no rest frame exists in which a photon can be treated as an observer, that conclusion is less dramatic than the idea of a frozen universe, but it is more exact. Light marks the boundary between the paths available to matter and the regions beyond ordinary causal contact. It connects distant events without carrying a valid clock between them. The result does not reveal an impossible view from light speed. It identifies the point where the language of viewpoints ends and the geometry of spacetime must take over. A spacecraft moving close to the speed of light would not see the surrounding universe arranged in the same way as an observer at rest with the stars. The change would not come from space itself bending around the vehicle in the ordinary sense. It would come from the way incoming light is transformed between different states of motion. Every star, planet, cloud, and distant galaxy is seen only because light reaches the observer from a particular direction. When the observer moves at relativistic speed, the measured direction of that light changes. This effect is called relativistic aberration. It causes more of the visible sky to appear concentrated toward the direction of travel, while the region behind is spread across a smaller and increasingly distorted part of the view. At low speeds, the effect is tiny. Earth experiences ordinary aberration because it moves around the Sun, but the change in apparent stellar position is small enough to require careful measurement. Near light speed, the same principle becomes dominant. Light arriving from the sides is shifted forward. Light arriving from partly behind can also appear closer to the forward direction. The faster the spacecraft moves, the more strongly the celestial sphere seems compressed into the area ahead. This compression does not mean that stars physically move toward one another, or that the spacecraft has entered a narrower region of space. It means that the angles at which their light reaches the moving observer have changed. The transformation follows directly from the invariance of light speed. In the rest frame of the surrounding stars, photons arrive along many different paths. In the spacecraft frame, those same photons must still travel at the speed of light, but their spatial directions are recalculated because the spacecraft is moving relative to the original frame. The result resembles the change in apparent wind direction felt by a moving vehicle. Though the physics is more exact and the comparison is limited, rain falling vertically relative to the ground may strike a moving window at an angle, because the vehicle has horizontal motion. Light behaves differently because its measured speed never changes. Yet the general idea of direction shifting with motion helps explain why radiation from a broad part of the sky is displaced forward. At extreme velocity, the forward concentration becomes severe. Stars that were separated by large angles in the galaxy's rest frame may appear crowded into a bright region around the direction of motion. Objects directly behind the spacecraft remain behind, but much of the surrounding sky is pushed toward the front. The boundary between the forward and rearward fields becomes increasingly compressed. A traveller would not simply see the same star map with every position shifted by an equal amount. The amount of aberration depends on the original direction of the light. Objects already near the direction of travel move less in apparent angle, while objects far to the side can shift dramatically. The pattern is continuous and mathematically ordered. As the spacecraft accelerates, the sky would seem to flow toward the point ahead, even though the distant objects remain nearly fixed in their own frame. This apparent movement would reverse during deceleration, with the field gradually spreading back toward its ordinary arrangement. A turn would produce a more complex redistribution, because the forward concentration would follow the new velocity direction, rather than the physical nose of the spacecraft, unless the two remained aligned. The visible universe would therefore be organized primarily by motion. Direction, brightness, color, and photon energy would all depend on the spacecraft's velocity relative to each source. Relativistic aberration is often described together with a headlight effect. Radiation is not only redirected forward but also concentrated in intensity. More photons arrive from a narrower range of angles, and their energies are altered by the relativistic Doppler effect. Sources ahead can become brighter, while sources behind can become dimmer. The exact appearance depends on the original spectrum of each object and on the sensitivity of the detector. Visible starlight may shift out of the visible range, while radiation originally outside human vision may move into it. A star cannot therefore be assumed to remain a visible point of the same color and brightness. Its light may be intensified, weakened, shifted into ultraviolet frequencies, or displaced toward infrared and radio frequencies. The geometric compression of the sky is only one layer of the transformation. A camera or human eye would also receive photons at altered rates and energies. These effects make the visual field ahead more than a simple cluster of displaced stars. It could become a region dominated by concentrated radiation, some of which would be invisible but physically important. The appearance of nearby objects would be especially complicated. A planet, spacecraft, or large structure passing at relativistic speed would not look like a flat object shortened along the direction of motion. Length contraction is a measurement made by recording the positions of the front and rear at the same time in a chosen frame. Vision does not perform that measurement directly. A photograph records photons that arrive at the camera together, but those photons may have left different parts of the object at different times. Light from the far side has a longer route than light from the near side. During those unequal travel times, the object continues moving. The image therefore combines different moments from the object's history. At relativistic speed, this can produce an apparent rotation or reveal surfaces that classical intuition would expect to remain hidden. This result is sometimes associated with the Terrell rotation. A rapidly moving sphere still appears broadly circular rather than compressed into a thin ellipse. Although markings on its surface are displaced in ways that make the sphere seem rotated, a cube can reveal parts of its side because light from different faces reaches the observer from different emission times. The object remains length contracted in the observer's measurements, but its photograph does not display that contraction in a direct and simple form. Visual appearance and measured geometry must therefore be kept separate. The same distinction applies to the outside view from a spacecraft. The contracted distance to a star is a statement about coordinates and simultaneous positions in the spacecraft frame. The star does not merely look closer because its image grows larger. A distant star remains an unresolved point, and a distant galaxy may remain very small in apparent size. The shortened distance belongs to the spatial measurement defined within the moving frame, while the visual image depends on angles, light travel time, Doppler shift, brightness, and detector response. A destination can be relativistically closer without appearing like a nearby object in the ordinary sense. Its apparent angular size may change only slightly until the spacecraft has covered a substantial part of the route. The traveller's shorter proper journey is real, but it should not be confused with a simple visual enlargement of the destination. A uniform field of background radiation would also be transformed. In a frame where radiation is nearly equal in all directions, a rapidly moving observer sees it become anisotropic, meaning directionally uneven. The radiation ahead is blue-shifted and appears hotter, while the radiation behind is red-shifted and appears cooler. The cosmic microwave background provides a real example at much lower velocity. The motion of the solar system relative to that background creates a measured dipole pattern, with one region slightly warmer and the opposite region slightly cooler. At near-light speed, this pattern would become far stronger. Radiation that is normally faint and low in energy could be compressed and shifted forward until it played a significant role in the spacecraft environment. The forward sky would become not only visually altered but thermally and radiatively different. At sufficiently high velocity, radiation from the cosmic background could be shifted into much more energetic parts of the spectrum. Light from ordinary stars could move beyond visible frequencies. The apparent narrowing of the sky would therefore occur together with a narrowing of safe observational conditions. Instruments designed for visible astronomy alone would give an incomplete and potentially misleading view. A realistic spacecraft would need detectors spanning radio, infrared, visible, ultraviolet, X-ray, and gamma-ray frequencies, together with shielding and careful calibration. The meaning of color would become especially frame-dependent. A source that emits most strongly invisible light in the galaxy's frame may be registered as ultraviolet or higher energy radiation ahead of the ship. Behind the ship, the same class of source may shift into infrared or radio frequencies and become difficult to detect without specialized instruments. The human visual system would show only a small portion of the full transformation. What appeared dark might still contain intense radiation beyond visible wavelengths. What appeared bright could be dominated by frequencies dangerous to biological tissue and electronics. The changed sky would therefore be a measurement problem as much as a visual one. Relativistic motion would also alter the apparent timing of events. Light from a variable star ahead could arrive in a compressed sequence, making its cycles appear faster. Changes behind could be stretched, appearing slower. An approaching source would seem to evolve more rapidly because successive wave crests and successive signals reach the spacecraft at shorter intervals. A receding source would seem to evolve more slowly. This effect is connected to the same Doppler shift that changes colour. A rotating beacon, an orbiting binary system, or a pulsing neutron star could display altered periods depending on direction and relative motion. The sky would not only be rearranged spatially, its processes would seem to run at different apparent rates. These changes do not represent the actual proper time experienced by the distant systems. They describe how signals are received by the moving observer. Correcting the measurements would allow the crew to reconstruct the rest frame behavior of the sources, but the immediate data would remain strongly transformed. Near light speed, perception becomes inseparable from relativistic analysis. The spacecraft would still occupy an ordinary local region of space-time. Inside the cabin, nearby objects would retain normal shapes. Clocks would run normally, and beams of light would move at the usual invariant speed in every direction. The unusual view would appear when radiation from the external universe entered that local frame. The sky ahead would contract into a smaller angular region. Sources would shift in colour and brightness, and background radiation would become increasingly concentrated. None of this would provide a visual picture of space at exactly light speed, because no massive observer can reach that state. It would instead reveal how the universe appears from a sequence of valid frames moving ever closer to the limit. The final scene would not be space collapsing into a point. It would be a progressively transformed field of incoming information, with direction, energy, and apparent timing all reorganized around the motion of the observer. At relativistic speed, the color of the universe would no longer be a stable property of the objects being observed. A star that appears yellow from one frame can appear bluer from another, while the same star seen from behind can shift toward red and then beyond visible light altogether. The effect comes from the relativistic Doppler shift, which changes the measured frequency of radiation when source and observer move relative to one another. In ordinary situations, the Doppler effect is familiar through sound. A siren approaching an observer is heard at a higher pitch, and the same siren moving away is heard at a lower one. Light follows a related principle, but with an important difference. Sound travels through a medium, while light in a vacuum does not require one. The relativistic Doppler shift therefore arises from the structure of spacetime and from the invariant speed of light, not from motion through a background substance. When a spacecraft moves toward incoming light, the wave crests reach it more frequently. The measured frequency rises, and the wavelength becomes shorter. This is called blue shift because visible light is pushed toward the blue end of the spectrum, though the shift can continue far beyond blue into ultraviolet, X-ray, or gamma-ray frequencies. Light arriving from behind undergoes the opposite change. The wave crests reach the spacecraft less frequently. The measured frequency falls, and the wavelength becomes longer. This is called redshift. Even when the radiation moves past red into infrared, microwave, or radio frequencies. The terms describe direction along the electromagnetic spectrum rather than a guarantee that the light remains visible. At modest speeds, the change is small. At a large fraction of light speed, it becomes one of the defining conditions of the journey. The size of the shift depends not only on velocity but also on direction. Radiation arriving directly ahead is affected most strongly. radiation arriving directly behind is shifted in the opposite direction. Light entering from the sides is transformed through a combination of Doppler shift and relativistic aberration, because the spacecraft measures both a new direction and a new frequency. As velocity rises, more of the sky is concentrated into the forward field, and more of its radiation is pushed toward higher energy. The same motion that narrows the apparent sky also raises the frequency and energy of radiation coming from it. This matters because photon energy is directly related to frequency. A higher frequency photon carries more energy than a lower frequency photon. Blue shift is therefore not merely a change in color. It changes the energy delivered to detectors, shielding, electronics, and living tissue. Visible light from a star can become ultraviolet radiation. Infrared radiation can enter the visible range. Microwave photons can be raised toward infrared or higher frequencies. At sufficiently extreme speeds, radiation that is harmless in the galaxy's rest frame can become ionizing in the spacecraft frame, meaning that it carries enough energy to damage atoms and molecules. The forward view would then represent an environmental hazard rather than only an altered image. The cosmic microwave background provides a useful example because it fills space in every direction and has a low temperature in the frame where it is nearly uniform. A moving observer already detects a slight difference between the forward and rearward directions. The region toward the observer's motion appears warmer, while the opposite region appears cooler. This dipole pattern is measured from Earth because the solar system moves relative to the background. A near light-speed spacecraft would see a much stronger version. Ahead, the background would be blue-shifted and concentrated. Behind, it would be red-shifted and weakened. The radiation would no longer resemble a nearly uniform microwave field. Its apparent temperature would become strongly directional, and the forward contribution could move into much shorter wavelengths. At sufficiently high speed, even this ancient low-energy radiation could become a significant source of heating and exposure. Starlight would undergo a similarly uneven transformation. Stars ahead could brighten because their photons arrive more frequently, carry more energy, and are concentrated by aberration into a smaller angular region. Stars behind could fade as their light is red-shifted and received at a lower rate. A familiar constellation would not simply change colour while keeping its original brightness. Some stars might shift out of the visible range toward ultraviolet and disappear from human sight even as their radiation becomes more energetic. Others might enter the visible band from infrared wavelengths and appear where no bright point was expected. The human eye would therefore provide an incomplete and sometimes misleading impression. A dark forward region could still contain dangerous ultraviolet or X-ray radiation, while a bright point might represent only a narrow visible portion of a much broader high-energy spectrum. Instruments would need to measure a wide range of incoming frequencies and reconstruct what each source would look like in its own rest frame. The Doppler shift also changes apparent timing. A source ahead that varies in brightness appears to change more rapidly because signals emitted at successive moments arrive closer together. A pulsar can appear to pulse faster. A source behind appears to evolve more slowly because the intervals between arriving signals are stretched. This effect is not the same as the time dilation assigned to the distant object. It is a signal reception effect produced by motion and changing arrival times. The distinction can be recovered through calculation, but the raw data received on board would combine frequency shift with altered apparent rates. Navigation systems would have to correct for both. A star catalogue built in the rest frame of the galaxy would not match direct observations without relativistic transformation. The same source might appear in a different direction, at a different brightness, with a different spectrum, and with a different apparent rhythm. The forward radiation hazard would not come from light alone. Interstellar gas and dust would also be transformed by the spacecraft's motion. Individual atoms ahead would strike with high kinetic energy, and their collisions with shielding could produce secondary radiation. Dust grains, though rare, could release severe energy on impact. Photons add another continuous burden. Unlike a single dust collision, background radiation arrives from an entire field and cannot be avoided by steering around isolated particles. Shielding must absorb, reflect, or redirect part of it. But every absorbed photon deposits energy. That energy becomes heat or initiates physical damage. A protective layer thick enough to reduce exposure adds mass, and added mass increases the energy required to accelerate the spacecraft. The problem therefore becomes circular. Higher speed raises the radiation energy. More radiation requires more shielding. More shielding requires more propulsion energy. Relativity does not prevent high-speed travel by one single rule alone. It creates a network of rising costs that becomes increasingly severe near the limit. The danger is strongest in the forward direction, which suggests that shielding would need to be directional. A spacecraft might place its heaviest protection at the front, with sensitive systems and inhabited areas deeper inside. Magnetic or electric fields could deflect charged particles, but they would not stop neutral dust or photons. Material shields could absorb radiation, yet at high energies they may generate showers of secondary particles. No single method removes the full environment. The spacecraft would need layered protection designed for particles, photons, heat, and secondary radiation at once. Even then, the safe speed could be limited well below the theoretical maximum allowed by relativity. The rearward sky would present the opposite condition. Radiation there would be redshifted and weakened, making distant objects dimmer and cooler in appearance. Some visible stars would move into infrared, and infrared sources would shift toward microwave frequencies. The spacecraft would receive fewer energetic photons from that direction, but it would also lose information. Rear-facing observations could become difficult because signals are stretched and reduced. Communication with the departure world would face the same effect. Radio messages sent from behind would arrive red-shifted. So receivers would need to account for the lower frequency and slower arrival rate. Messages sent forward from the spacecraft toward its destination would be blue-shifted in the destination frame if the craft were approaching. Communication systems would need to choose frequencies carefully so that the transformed signal remained within the intended detection band. These shifts also affect how scientific instruments interpret the universe. Color would cease to be a simple clue to the temperature or composition of a source unless the Doppler factor had first been removed. An apparently blue source might not be intrinsically hot. It might only be approaching at high relative speed. An apparently red source might not be cool or cosmologically distant. It might lie behind the moving observer. Relativistic Doppler shift does not destroy information, but it redistributes that information across frequency, direction, intensity, and time, with sufficiently capable instruments. The original properties of many sources could be reconstructed, yet the immediate physical effects could not be calculated away. A photon blue-shifted into an ionizing range deposits the energy it has in the spacecraft frame. Radiation damage remains real even when its origin is understood. The same is true for heating, detector saturation, and electronic failure. Near light speed, observation and exposure become inseparable. Every signal from the forward universe arrives as both information and energy. The external radiation field becomes part of the propulsion, shielding, and survival problem. Long before a massive spacecraft could reach the cosmic limit, the transformed spectrum of ordinary space would reveal how extreme its motion had become. A human observer aboard a spacecraft moving close to the speed of a light would not see a simple version of the familiar night sky rushing past. The stars would not stretch into long white lines. and the forward view would not automatically become a bright tunnel. Those images belong mainly to artistic convention. A real relativistic sky would be transformed by the combined effects of aberration, Doppler shift, intensity change, and the limited range of human vision. The result would depend on the spacecraft's velocity, its direction of travel, the spectra of the objects ahead, and the sensitivity of the eye or instrument receiving the light. At moderate relativistic speeds, recognizable star patterns could still be reconstructed, but their positions would be displaced. As the velocity increased, the constellations would lose their familiar shapes because their light would arrive from new angles. Stars originally spread across the sides of the sky would appear drawn toward the direction of motion. The forward hemisphere would seem increasingly crowded, while the rearward hemisphere would become more open and depleted. The transformation would be smooth rather than chaotic. Every apparent position would follow a precise relativistic rule. Yet the sky would cease to resemble the map learned from Earth. The brightest concentration would not necessarily lie exactly at the geometric center of a window, unless the spacecraft's velocity and viewing direction were perfectly aligned. The defining direction would be the spacecraft's motion through the local stellar frame. If the vehicle rotated while continuing along the same trajectory, the concentration of light would remain tied to the velocity vector, not to the walls of the cabin. A window facing sideways could therefore receive a sky that still appeared displaced toward the direction of travel. Navigation by unaided sight would become difficult because the visible field would no longer correspond directly to ordinary stellar coordinates. A computer would need to transform each observed direction back into the rest frame of the surrounding stars. Without that correction, a familiar star might appear far from its catalogued position, and objects originally separated by a large angle might seem close together. Brightness would change at the same time. Radiation ahead would arrive at a higher rate and with greater energy, while aberration would concentrate it into a narrower field. Some stars would become more intense. Others would vanish from visible sight because their light had shifted beyond the range detected by the eye. A star does not remain visible merely because its total radiation becomes stronger. If most of its visible output is shifted into ultraviolet frequencies, the eye may see less even while the spacecraft receives more energy. The opposite can also occur. A cool star or warm dust cloud that emits strongly in infrared may be blue shifted into the visible band and become newly apparent. The resulting sky would contain unfamiliar sources created not by new objects, but by radiation moving into the narrow window of human vision. Color would therefore become an unreliable guide to the intrinsic nature of a star. A red star ahead could appear white or blue. A blue star might shift into ultraviolet and become faint or invisible to the eye. Behind the spacecraft, visible stars would drift toward red and then into infrared, fading from direct sight. The rearward sky could become optically dark long before it became physically empty. Radio, microwave, and infrared detectors would still find signals there. But an unassisted observer might see only a reduced field of dim red points. The forward sky could also appear darker than expected if much of its radiation had shifted beyond visible light. A display that converted ultraviolet, X-ray, infrared, and radio data into artificial colors would show a far richer scene than a transparent window. For practical travel, such a display would be essential. It could correct aberration, restore each source to its estimated original color, reduce dangerous brightness, and present a stable navigation map. The actual radiation outside the spacecraft would remain transformed, but the information could be translated into a form the crew could understand. Without such correction, the view would change continuously during acceleration. At the beginning of the journey, the sky would look nearly normal. As speed increased, constellations would lean forward, their shapes narrowing in the direction of motion. Stars near the sides would drift across the field. Their colours would change at different rates depending on their original spectra and angles. Some points would brighten temporarily as their strongest emission entered the visible range, then fade as that emission shifted past it. The forward concentration would become smaller and more intense, but it would not be a single uniform patch. Nearby stars, distant galaxies, glowing gas, and background radiation would each respond according to their own spectral properties. Dark gaps could remain between sources, while invisible high-energy radiation filled the same region. The visual impression would therefore be less like a solid beam and more like an unfamiliar star field compressed into a restricted part of the sky. Stellar motion across the view would also differ from the common image of objects racing backward. Distant stars would not sweep past rapidly, merely because the spacecraft moved quickly. Their great distances keep their angular motion small over short periods. Nearby stars would change position more noticeably through parallax, while distant galaxies could remain almost fixed in angle even during a long journey. What changes immediately is not the physical location of the stars but the direction from which their light is measured. Acceleration would make the entire field flow toward the forward point. Once the spacecraft reached constant velocity, that large-scale pattern would settle. The altered star map would remain stable apart from the spacecraft's changing location, the proper motions of the sources, and variations in their light. Deceleration would reverse the aberrational flow. Constellations would gradually spread away from the forward direction and return toward the arrangement associated with the destination frame. This changing map could make acceleration itself visible. An onboard observer could infer changes in velocity by tracking how known sources shifted across the sky. Although practical instruments would perform the calculation far more accurately than the eye, the apparent brightness of variable objects would carry another distortion: pulsating stars, eclipsing binaries, rotating neutron stars, and explosive events ahead would seem to evolve more rapidly because their successive signals would arrive in compressed intervals. Behind the spacecraft, the same kinds of processes would appear slowed and stretched. A supernova observed ahead could brighten and fade over a shorter received duration than it would in the source's rest frame. A pulsar's rhythm could accelerate. These changes would not show that the distant systems were physically aging faster. They would show that the motion of the observer alters the rate at which information arrives. Correcting the Doppler factor would recover the source's own timing, but the immediate visual experience would remain compressed in front and extended behind. Light from the destination would therefore present an accelerated sequence of change during approach, while light from the departure region would arrive increasingly delayed, red-shifted and slowed in apparent rhythm. The spacecraft would not see Earth running in simple slow motion throughout the entire journey. The received image would depend on the ship's motion, distance, and turnaround history. Signals from Earth would take time to catch up, and their frequency would change as the spacecraft moved away or later returned. The same distinction applies to the wider universe. What appears on a display at any moment is a collection of old signals transformed by motion, not a direct view of distant events occurring at one shared present. Human vision would add biological limits to the physics. The eye adapts to brightness over time, but it cannot detect most of the electromagnetic spectrum and cannot safely receive intense ultraviolet or ionizing radiation. A transparent forward window would provide little practical value at extreme speed and could create a dangerous weak point in the shield. Cameras placed behind protected apertures would be more realistic. Their data could be filtered, delayed, and remapped before reaching the crew. Bright sources could be dimmed. Invisible frequencies could be assigned artificial colors. Aberration could be removed to create a stable rest-frame sky, or preserved to show the true incoming direction of radiation. Several displays might be needed because no single image could represent direction, original spectrum, received energy, and radiation hazard at once. A calm, Earth-like star field shown inside the cabin would therefore be a reconstruction rather than the direct optical scene outside. The underlying view would remain scientifically ordered but unfamiliar. Stars would gather toward the path ahead, shift in colour according to direction, change in apparent brightness, and display altered rhythms. Some familiar objects would disappear from human sight, while unexpected sources emerged from infrared or other wavelengths. The rear would lose visible detail, and the front would become increasingly dominated by radiation that the eye could not safely or fully perceive. Near the light-speed boundary, the universe would not become visually meaningless. It would become dependent on interpretation. Instruments and relativistic calculations would be required to separate the original properties of the sky from the changes created by the observer's motion. What the crew saw on a screen could be made familiar, but what reached the spacecraft would be a transformed field of light carrying the exact signature of its velocity through space-time. The twin paradox begins with a simple comparison between two clocks that start together, separate, and later meet again. One clock remains on Earth while the other travels aboard a spacecraft at relativistic speed, turns around, and returns. When the clocks are brought back to the same location, the travelling clock records less elapsed time. A person who made the journey would therefore be younger than a person who stayed behind. The word paradox survives because the result can seem contradictory at first. During uniform motion, each observer can describe the other clock as running slowly. If the traveller sees Earth's clock slow down, and Earth sees the traveller's clock slow down, it may appear that both should be younger at reunion. Special relativity avoids that contradiction because the two paths are not equivalent. The Earthbound observer remains approximately within one inertial frame for the comparison, while the traveller changes velocity, reverses direction, and moves from one inertial frame to another. The histories through space-time are different, and the amount of proper time accumulated along them is different as well. Proper time is the time measured by a clock carried along a particular path. Between the departure and reunion events, Earth follows one path and the spacecraft follows another. In ordinary Euclidean geometry, a straight route is the shortest distance between 2 points. In the geometry of spacetime, the corresponding inertial path between two time-like separated events accumulates the greatest proper time. The traveller's route includes change of direction in spacetime, so it contains less proper time than the route of the observer who remains at rest relative to the departure and return location. The age difference is not produced by a temporary malfunction during the turnaround. Acceleration is important because it changes the traveller's frame and breaks the symmetry. But the reduced aging can be calculated from the entire path. Even if the turnaround is brief, the difference in elapsed time can be large when the outward and inward legs are long and fast. Suppose a spacecraft departs from Earth at a speed close to light speed and travels toward a distant star. Earth observers say that the onboard clock runs slowly throughout the outward journey. When the spacecraft reverses direction, they continue to say that its clock runs slowly during the return. From this frame, the explanation is direct. The traveller covers a long distance at high speed, and the moving clock accumulates less time before reunion. The traveller's description requires more care. During the outward leg, Earth is receding, and the traveller assigns a slow rate to Earth's clock. During the inward leg, Earth is approaching, and the traveller again assigns a slow rate to the Earth clock while using a new inertial frame. The crucial change occurs in the assignment of simultaneity during the turnaround. The set of distant Earth events regarded as simultaneous with the traveller's present shifts forward. In the traveller's description, a substantial amount of Earth time can become newly assigned between the outward and inward frames. This does not mean that Earth physically jumps through time or that its clocks suddenly race in a locally observable way. It means that the traveller has changed the rule used to define which distant event on Earth is happening at the same time as the turnaround. Because simultaneity is relative, changing frames changes the distant time coordinate. The asymmetry is therefore real and measurable. Only the traveller undergoes the frame change needed to leave and return, while the stay-at-home observer does not follow the same sequence of inertial states. A signal-based account leads to the same result. During the outward journey, signals from Earth arrive red-shifted and at a reduced rate. The traveller sees Earth's broadcasts arriving slowly because the distance is increasing. After turning around, later signals arrive blue-shifted, and at a higher rate because the traveller is moving toward Earth. The slow arrival of signals on the outward leg and the rapid arrival on the inward leg combine to show a larger total span of Earth history than the traveller personally experiences. Earth sees a related pattern in signals from the spacecraft. The two descriptions differ in detail because of light travel time, but once signal delay is separated from clock rate, they agree on the final age difference. This is one reason the twin paradox is not merely a visual effect. The clocks can be placed side by side after the journey. Their readings do not depend on interpretation at that point. The travelling clock shows less elapsed time. The same principle applies to any physical process carried on board. The traveller's heartbeat, metabolism, memory, and biological aging proceed normally in the local frame. Nothing feels slowed inside the spacecraft. The difference appears only when the traveller returns and compares the accumulated time with Earth. If 10 years pass aboard the ship while a much longer period passes on Earth, the crew has not lived through the missing years in a slowed or unconscious state. Those years simply do not belong to the proper time along the spacecraft's path. This creates a one-way form of travel into the future. A crew could depart, experience a relatively short voyage, and return to an Earth that has aged much more. The effect does not allow the crew to come back before departure, or to send information into the past. It changes the amount of time accumulated between shared events, not the causal order of those events. The practical scale of the difference depends on speed and distance. At moderate velocity, the age gap is small. As the spacecraft approaches light speed, the Lorentz factor grows, and the traveller's elapsed time can become much shorter than Earth's. A destination hundreds of light-years away would still require hundreds of years or more for a round trip according to Earth clocks, if the vehicle remained below light speed and spent time accelerating and slowing. For the crew, length contraction would reduce the distance during the high-speed legs, allowing the same journey to occupy far less proper time. In principle, a voyage spanning many generations on Earth could fit within a much smaller fraction of one human lifetime aboard the craft. The idea remains consistent with the speed limit because Earth still measures the spacecraft moving below light speed, and the crew measures a contracted distance rather than a superluminal velocity. The twin paradox can also be understood without an abrupt turnaround. A spacecraft may accelerate smoothly, follow a curved path, or use a planet or star to change direction. General relativity may be needed for a complete description if strong gravity is involved, but the final comparison still depends on proper time along each world line. A world line is the path an object traces through space-time. Different world lines connecting the same departure and reunion events can contain different amounts of proper time. Acceleration identifies that the paths differ, but the clock reading is determined by the full space-time route. This is why replacing the traveller with several inertial observers does not remove the result. One outbound spacecraft can pass its clock reading to an inbound spacecraft without either performing a long acceleration. Together they form a path with less proper time than the Earth observer's path, and the final clock comparison remains the same. The paradox also survives more realistic complications. Earth is not perfectly inertial because it rotates, orbits the Sun and moves through the galaxy. A real spacecraft would accelerate over finite periods. Gravitational fields would alter clock rates as well. These effects can all be included in a more complete calculation. They do not erase the basic result. If two clocks leave the same event, follow different paths through space-time, and reunite, they can record different elapsed times. Experiments with atomic clocks, fast-moving particles, and satellite systems confirm the underlying principles. The age difference is not limited to thought experiments. It is a direct consequence of how motion and gravity shape time. For interstellar travel, however, time dilation solves only the duration experienced by the crew. It does not solve the energy requirement, the radiation environment, navigation, communication delay, or the social consequences of returning to a world that has advanced far beyond the date of departure. The travellers may cross a great distance within their own lifetime, yet they cannot prevent centuries from passing elsewhere if the route is long enough. They may arrive at a destination whose signals left before the mission began, and any message sent home will still move at light speed. Relativistic travel reduces personal elapsed time without creating a shared shortcut for the civilizations at each end. The crew can shorten the journey for itself, but not for the external universe. This distinction gives the twin paradox its lasting importance. It is not only a puzzle about clocks. It shows that aging, duration, and distance are local features of a path through space-time. Two people can leave the same event, reunite at another, and have lived through unequal amounts of time without either clock being wrong. The difference is not hidden in perception. It is recorded in matter, memory, and biology. Near light speed, the separation between personal time and distant time becomes large enough to reshape the meaning of a journey. Relativity permits the traveller to reach far into the future of the departure world, but it keeps every stage of that voyage inside the causal limits set by light. The light speed boundary remains firm in every experiment that tests ordinary matter, radiation, and information. Yet theoretical physics continues to examine whether space-time itself contains routes that do not resemble ordinary motion through space. These ideas are often grouped together as ways to go faster than light, but they are not all the same claim. Some propose hypothetical particles that always move beyond the limit. Others use unusual geometries in general relativity, where the distance between two regions changes without a traveller locally outrunning a nearby beam of light. Still others arise from quantum theory, where correlations and tunnelling can appear to connect distant events in unfamiliar ways. The central question is not simply whether an equation can contain a superluminal quantity. It is whether a complete physical process can carry matter or controllable information from one place to another faster than light while remaining stable, causal, and compatible with known laws. That standard is much harder to meet. Tachyons are one of the oldest speculative possibilities. They are hypothetical particles defined to move faster than light in every ordinary inertial frame. A tachyon would not begin below light speed and accelerate through the boundary. Just as a photon cannot be placed at rest, a tachyon would belong to a separate class of motion and could not be slowed below the light speed limit. In simple, relativistic descriptions, its energy would behave in an unfamiliar way. Adding energy could reduce its speed toward light speed from above, while removing energy could make it move faster. No confirmed particle has ever shown this behavior. More importantly, the concept creates severe problems with causality, because observers moving relative to one another divide space and time differently. A signal that travels faster than light in one frame can be described in another frame as arriving before it was sent. With carefully arranged exchanges between moving observers, a reply could return to an event earlier than the original transmission. The result would not be a harmless disagreement about timing. it could create a closed causal loop in which information influences its own past. Some speculative theories attempt to restrict tachyon behavior or introduce a preferred frame that protects causal order, but doing so changes the symmetry at the foundation of special relativity. In modern field theory, the word tachyon often has a different technical meaning. A tachyonic term usually signals that a proposed state is unstable and will reorganize into a more stable state. It does not necessarily represent a usable faster-than-light particle crossing space. The appearance of such a term can indicate that the mathematical description has been expanded around the wrong vacuum, meaning the wrong lowest energy configuration. Once the system settles into a stable configuration, ordinary causal propagation can remain intact. This distinction matters because a faster-than-light label inside an equation does not automatically provide a superluminal object. Wormholes take a different approach. General relativity allows space-time to curve, and some solutions contain tunnels linking regions that would otherwise be far apart. A traversable wormhole could, in principle, provide a short internal route between two distant mouths. A traveller passing through it might reach the other region before a light signal travelling through ordinary external space. Locally, the traveller would remain below light speed. The apparent shortcut would come from the geometry, not from motion through nearby space faster than light. The difficulty is that a mathematical geometry is not yet a physical construction. The simplest wormholes are either non-traversable, unstable, or hidden behind horizons. Keeping a throat open for safe passage appears to require stress and energy arranged in forms unlike ordinary matter. Many theoretical models rely on negative energy density, a condition in which the local energy is lower than the surrounding vacuum reference. Quantum theory permits limited negative energy effects in carefully constrained situations, but known examples are small, temporary, and balanced by restrictions that prevent unlimited use. No established mechanism can create and maintain a large human-scale traversable wormhole. Even if one existed, moving its mouths relative to one another could turn it into a path between different times as well as different places. The same shortcut that defeats ordinary distance could threaten causal order. Some arguments suggest that quantum effects would become strong enough to destroy the configuration before a time loop formed. But there is no complete theory of quantum gravity that settles the question. Warp geometries are another attempt to alter distance rather than exceed light speed locally. In the best-known proposal, a region containing a spacecraft remains locally calm, while space-time contracts ahead and expands behind. The region itself moves relative to distant observers, even though the spacecraft inside never locally outruns light. General relativity permits the geometry as an exact mathematical solution under chosen conditions. The physical requirements are far less encouraging. Standard versions demand negative energy arranged around the moving region, often in enormous quantities or in distributions that do not resemble any known material system. Later modifications can reduce some demands or change the shape of the geometry, but reducing one difficulty does not establish a workable engine. Questions remain about how the region would be created, accelerated, controlled, and stopped from inside. Some versions develop horizons that isolate the spacecraft from the front edge of the distortion, making it unclear how the crew could direct its own motion. Others may accumulate energetic particles or radiation along the boundary and release them dangerously when the geometry changes. The mathematical possibility, therefore, remains far from a demonstrated physical technology. General relativity also allows distant galaxies to separate faster than light, because cosmic expansion changes the scale of space between them. During inflation, an early period of extremely rapid expansion, widely separated regions could recede from one another at effective rates greater than the local speed of light. These cases do not provide a method for a nearby spacecraft to cross its local light cone. Every freely falling observer still measures local light moving at the invariant speed, and every massive object nearby remains slower. The superluminal quantity describes the growth of distance across a changing global geometry. It cannot be converted directly into an engine simply by pointing a vehicle toward a distant galaxy. A similar caution applies near black holes, where coordinate choices can make speeds appear unusual. A distant observer may describe in falling matter as slowing near a horizon, while a freely falling observer crosses the same region in finite proper time. Neither description allows matter to pass a local light beam in the same direction. Coordinate speeds can vary because coordinates are labels, but locally measured causal limits remain intact. Quantum mechanics creates a different set of misunderstandings. Entangled particles can produce correlations that cannot be explained by ordinary local hidden instructions, and those correlations can appear without a signal travelling between the measurements in the classical sense, yet the measurement outcome at either location is not controllable. Useful information appears only when the results are later compared through an ordinary causal channel. Quantum teleportation also requires a classical message, so it cannot transmit a state faster than light. Tunneling experiments can produce pulse peaks or mathematical velocities that seem superluminal, but the front of a genuinely new signal does not provide controllable information outside the light cone. Wave reshaping, group velocity, and statistical interpretation can create apparent advances without carrying a chosen message into the past. These examples show why the word speed must be defined carefully. Phase speed, pattern speed, coordinate speed, and information speed are not interchangeable. The boundary enforced by relativity concerns local causal influence. That boundary may eventually be understood as part of a deeper theory. General relativity treats space-time as a smooth geometry, while quantum theory describes nature through fields, probabilities, and discrete interactions. Both theories are extremely successful within their domains, but they do not yet form one complete description under conditions where gravity and quantum effects are simultaneously extreme. Black hole interiors, the earliest universe, and the smallest meaningful scales expose this gap. A future theory of quantum gravity may reveal that space-time is emergent, granular, relational, or built from structures not yet recognized. Such a theory could change the language used to describe distance and duration. It might explain why the speed of light has its particular causal role, why Lorentz symmetry is so accurate, and whether space-time topology can change through physical processes. None of that implies that faster-than-light travel will become possible. A deeper theory may reinforce the limit rather than remove it. The most reliable conclusion remains the one supported by established physics. Massive objects can approach light speed but cannot reach it through finite acceleration. Light-like signals define the causal boundary. Wormholes and warp geometries exist as theoretical constructions with unresolved physical requirements. Tachyons remain hypothetical and causally difficult. Quantum correlations do not provide controllable superluminal communication. The open problem is therefore narrower than the idea of an undiscovered engine waiting beyond current technology. It concerns the origin and full meaning of the boundary itself. Space and time change with motion. Gravity reshapes their geometry, and quantum theory suggests that the smooth structure may not be fundamental. Even so, every confirmed local process preserves the same causal order around the speed of light. The remaining uncertainty lies not in whether ordinary matter can ignore that limit, but in why the universe is organized so consistently around it, and whether a deeper account of space-time will show the boundary to be an imposed rule, an emergent consequence, or the defining condition that allows cause and effect to exist at all. The speed of light does not simply mark how fast radiation moves. It defines the shape of cause and effect, the limits of motion, and the way space and time divide themselves for different observers. As velocity rises, clocks no longer agree, distances no longer remain fixed, and distant events no longer share one universal present. These changes are not failures of measurement, they are the measurements. They reveal that space and time are not separate backgrounds, but parts of one structure that responds consistently to motion. Light occupies the boundary of that structure without carrying a valid rest frame of its own. Matter can approach the boundary, but every additional gain demands more energy, stronger protection, and greater control. For a traveller moving near that limit, distant journeys can become shorter, and personal time can pass more slowly, while the outside universe continues through years, centuries, or longer spans. The sky itself would change, with stars shifting in direction, colour, brightness, and apparent rhythm. Yet beneath every transformation, the same rule remains intact. No local observer sees light exceeded. No confirmed signal escapes the causal order protected by that speed. Wormholes, warp geometries, and hypothetical faster-than-light particles remain useful tests of theory, but none has become a demonstrated route through the universe. The deeper mystery is therefore not only whether the limit can be crossed, it is why reality is arranged around it so precisely. Whatever space-time ultimately proves to be, the speed of light remains one of the clearest signs that the universe is not built from space and time separately, but from a deeper relationship between motion, distance, duration, and causality.